Good morning, ladies. We are starting our new section, Ideal Gases and Thermal Properties, and this is a chemistry section. Now, once again, we are starting with a bit of revision. So, the kinetic theory is definitely something that you have learned of before, and we can use the kinetic theory to describe matter. And as you all know, according to the kinetic theory, all matter is made up of particles. The particles are in constant motion, which means that the particles have kinetic energy, and there are forces of attraction and repulsion between particles. The forces of attraction are, of course, the forces that keep particles together, and the forces of repulsion will become evident when particles start moving too close together. Now, just to say a little bit more about the particles are in constant motion, we also just need to know that not all the particles move at exactly the same speed. So it is actually best to describe the average kinetic energy of a substance because we actually use the average speed of the particles when we calculate the kinetic energy. And that is also the reason why temperature of a substance is described as a measure of the average kinetic energy of all the molecules in that substance because all the particles actually move at different speeds. Then, this is also something that you've done. We can use the kinetic theory to describe solids, liquids, and gases. So let's take a look at solids. In solids, we know that the forces of attraction are very strong. That is why solids have a definite shape. In solids, the particles are arranged in a definite pattern, which is sometimes also described as a crystal lattice. Even in solids, the particles are in constant motion. They vibrate around fixed positions. And even with these vibrations, not all the particles move at exactly the same speed. And then lastly, we also know that solids are difficult to compress because the particles are so close together. Oopsie. And then if we take a look at liquids, particles have more energy compared to solids. In liquids, the forces of attraction are weaker if we compare them with the forces in solids. In liquids, the particles have more freedom of movement. The particles can actually move past each other. There are still forces of attraction, and they are still strong enough to keep the particles together. And then also we know that liquids don't have a fixed shape and that a liquid takes up the shape of the container. Now, this freedom of movement of molecules in a liquid ensures that they can actually slide over each other, and this is what makes it possible for a liquid to flow. Now, even in a liquid, just like a solid, the individual particles move at different speeds, and just like with a solid, it is difficult to compress a liquid because the molecules are still close together, and liquids exert a pressure on any object that you place in the liquid as well as on the sides of the container. And this pressure exerted on an object is actually something that I am sure you have experienced, because if you jump into a pool and you are surrounded by water, you can actually feel the pressure exerted on your body by the water. And then lastly, if we look at gases, here the particles have much more energy. They move much further apart. There's very little forces of attraction between them. The molecules in a gas have a lot more freedom, and that is why if you fill a container with a gas, it actually fills the whole container. Even in gases, the particles move at different speeds. Compared to solids and liquids, it's easier to compress a gas because the molecules are so far apart to start with. In gases, the particles collide with an object placed in the gas, and the particles will also collide with the sides of the container, and this is the reason why gas particles exert pressure. And then just a little bit more about that pressure. It is actually caused by the force that the particles exert on the sides of the container when they collide with the sides of the container. And that is why pressure is described as force per unit area on the surface as a result of the collisions of the particles with that surface. Then, if you look on page 138, activity 7.1, there is a table that you can complete, and by doing that, you will then actually have a very nice summary of everything that I have said up to here. All right. Then, as I said, this chapter is all about gases. So let's take a look at what else you need to know. Ideal gases. Now, the ideal gas is a hypothetical gas. In other words, there isn't a gas on the periodic table called the ideal gas. This is a hypothetical gas that obeys all the gas laws. So what we do when we describe gases, we use a model to describe a typical gas. And this typical gas displays the properties that gases normally display. And this is then described as the ideal gas model. So this ideal gas is a typical gas. Now, there are some important aspects of the ideal gas model that you need to know about. And for now, I am just going to go through them very quickly as theory that you can take a look at. And then as we go through the rest of the chapter, I will concentrate on a couple of these points when we get to it, especially when we are busy with calculations. So let's just take a look at the most important aspects of the ideal gas model. So, according to this, gases consist of particles that are in constant motion in all directions. Number 2, particles are very small and together they do not contribute to the volume of a gas. So the volume of a gas is actually determined by the volume of the container in which you place the gas, not the particles of the gas itself. Number 3, particles exert no forces on each other, nor on the sides of the container, except when they collide with each other and the sides of the container. Number 4, collisions between gas particles and between particles and the sides of the container are described as being perfectly elastic, meaning absolutely no energy is lost during the collision. So however much energy the particle has before it collides with the side of the container, it has exactly that same amount of energy after its collision. Number 5, all ideal gas molecules are identical. Number 6, the temperature of the gas is a measure of the average kinetic energy of the particles. Number 7, pressure exerted by the particles is the result of the collisions of the particles with the sides of the container. And number 8, the gas exerts no pressure at, and this is 0 Kelvin, and no motion of particles at this temperature as well. So 0 Kelvin is described as absolute zero, and this is the lowest possible temperature. So just to say a little bit about that, the Kelvin temperature scale is the temperature scale that we use when we are busy with gases. So in all the calculations where temperature is involved in this section, temperature must be in Kelvin. And as I've said before, when we actually get to the calculations, I'll remind you about this again. But what we will probably do is give the temperature in degrees Celsius to see if you remember that you have to convert to Kelvin. And this is how it's done. To convert degrees Celsius to Kelvin, and it's not degrees Kelvin, it's just Kelvin, the number to remember is 273. It does appear on the data sheet as well. And then to differentiate between temperature in degrees Celsius and temperature in Kelvin, we use a capital letter T for temperature in Kelvin and a small t for temperature in degrees Celsius. So if I take the Kelvin temperature and I minus 273, that will give me the temperature in degrees Celsius. Or if I take the temperature in degrees Celsius and I add 273, that will give me the temperature in Kelvin. So if we go back to our 0 Kelvin that we mentioned previously, the equivalent of that would be minus 273 degrees Celsius. So absolute 0 Kelvin, is the equivalent of minus 273 degrees Celsius. Right, ladies, and I think that is enough for today. Thank you.